Look up on a clear night, and the scale of the universe feels infinite. Yet for most of modern history, the physical and social spaces permitted to the women trying to study it were painfully claustrophobic. For centuries, studying the stars came with absurd earthly conditions. Women had to conduct research in secret, they endured observatories with no public bathrooms, or simply marry a prominent male astronomer just to get in the door. A few found a way through. Maria Mitchell discovered a comet in 1847, and Caroline Herschel cataloged thousands of nebulae. But even these pioneers were often relegated to polishing telescope lenses or acting as unpaid assistants. Despite extreme systemic barriers blocking them from the telescope, a small group of marginalized women forced the universe into focus, drawing the exact blueprints of modern astrophysics we still use today. In the late 19th century, the Harvard Observatory found a loophole. Director Edward Pickering needed to process massive amounts of raw astronomical data. Since women were forbidden from operating the physical telescopes, they could be hired cheaply as human computers to crunch the numbers. One of these computers was Henrietta Swan Leavitt. She spent her long days staring at glass photographic plates, comparing the true brightness of specific stars that pulsed over time, a class of variable star known as Cepheids. This diagram shows what Leavitt noticed, a direct mathematical link between how frequently a star blinks and its actual peak brightness. By knowing a star's true brightness, astronomers could compare it to how dim it appeared from Earth, giving them an accurate cosmic ruler to measure the vast distances to other galaxies. At the same time, another computer named Annie Jump Cannon was tasked with making sense of the light coming from over 1,000 different stars. Cannon realized that by observing a star's color spectrum, she could determine its exact temperature. She sorted them into a system categorized by the letters O, B, A, F, G, K, and M, ranking them from blue hot down to red cool. They were physically barred from looking through the lens, yet these women became the first to successfully decode the raw data of the cosmos. By the mid-20th century, female astronomers began moving beyond raw data collection and into deep theoretical physics. But the institutional walls remained high. While writing her doctoral dissertation, Cecilia Payne-Gaposchkin made a radical proposition. The accepted science of the time stated that stars were made of the same heavy elements as Earth. She looked at the stellar spectra and proved that stars are actually composed almost entirely of hydrogen and helium. Her male peers at Princeton immediately dismissed her findings as clearly impossible. She was pressured to downplay her own research, only for those same men to begrudgingly accept the exact same conclusion years later. Decades later, astronomer Vera Rubin encountered the exact same kind of skepticism while she was meticulously tracking the rotation of distant galaxies. This diagram illustrates the problem Rubin observed. According to the laws of physics, stars on the outer edge of a galaxy should orbit slower than those near the dense core. But Rubin measured outer stars moving at the exact same velocity as the inner stars. The only mathematical explanation is that an unseen mass, dark matter, is gravitationally holding the whole galaxy together. Across the Atlantic, a graduate student named Jocelyn Bell Burnell noticed strange anomalies in her radio telescope data. She tracked these repetitive radio pulses and correctly identified them as rapidly spinning neutron stars, what we now call pulsars. But because she was a graduate student, the Nobel Prize Committee bypassed her entirely, awarding the prize for her discovery to her male advisor instead. The math was undeniable, but these women proved that fighting the bias of scientific consensus often requires more energy than the science itself. Eventually, the sheer weight of these discoveries fractured the institutional ceiling, allowing women to take executive command of space exploration. In 1961, Nancy Grace Roman became the very first chief of astronomy at a newly established agency called NASA. At the time, astronomers relied on balloons and sounding rockets for high-altitude observation. Roman spent years fiercely lobbying Congress, demanding funding for a massive permanent observatory that would live entirely in space. Her relentless political push resulted in the approval and eventual launch of the Hubble Space Telescope. Down on Earth, astronomers like Andrea Ghez began utilizing advanced facilities like the Keck Observatory, using new adaptive optics to peer directly through the thick, obscuring dust at the center of the Milky Way. By cutting through the interference, Ghez observed stars moving at ultra-high speeds around a single compact point. This provided conclusive proof of Sagittarius A star, the supermassive black hole anchoring our galaxy. For this work, Ghez was awarded the 2020 Nobel Prize in Physics, cementing the reality that women had moved from the hidden background of astronomy to its most celebrated forefront. Because of these scientists, the night sky evolved from a flat canopy into a deeply measurable cosmos. Now, their legacy is physically etched into the map of the universe itself. Take the work of Carolyn Shoemaker, who identified dozens of new comets and asteroids. In 1993, she co-discovered a fragmented comet on a collision course with Jupiter. When it finally plunged into the planet's atmosphere, it became the first celestial event of its kind ever observed by humanity, and it forever bears a woman's name, Comet Shoemaker-Levy 9. This map will expand again in 2027, when NASA launches its next flagship observatory, the Nancy Grace Roman Space Telescope, tasked with exploring dark energy and exoplanets. And today, leaders like Andrea Ghez and Jocelyn Bell Burnell are actively using their Nobel and Breakthrough Prize money to fund scholarships for underrepresented groups in physics. The universe is too complex to be decoded by a single demographic. By actively dismantling the barriers for the next generation of scientists, we guarantee the continued discovery of our cosmos.